So we want to look at some more numerical methods for evaluating or estimating definite integrals. In the last video we looked at the trapezoid rule. In this video we look at Simpson's rule. Now Simpson's rule, as with the others we've seen so far, you're going to take, well, you've got a definite integral that you're trying to evaluate or estimate. So you're going to take the interval from A to B and cut it up into a bunch of pieces. This time we have to make sure that the number of pieces is even, because I'm going to take them two at a time here. So you've got your function, whatever it looks like up above, and you're taking 3 points in a row here, so two intervals, and you're going to evaluate the function at those points, and then you're going to connect those points by a parabola. So a quadratic function would be right through here somewhere. And then you're going to move on to, so I've used this one and this one. Oh, you're going to find the area underneath that parabola. Then I'm going to move on to the next pair. So this interval and that interval, using this point, and this point, and use those to come up with the equation of a parabola and find the area underneath that parabola. Now, I say you've got to do all these things, but Simpson has actually already done these things. This is probably not Bart. So as long as you've got an even number, you can take them in pairs going all the way across. And what Simpson showed, and the book shows this as well, I don't know if it's worth our time to go through that. You can read it in the book. That the area, let's just say one of these things here. So this is A, this is x1, this is x2. So this first area here is going to be 1/3 times delta x, and of course delta x is the same as it's always been, b minus a over n, times, now you want the function value at a plus 4 times the function value at x1 plus the function value at x2. Then you move over to the next one, a2, and a2 is going to equal 1/3 delta x times, well, it's essentially the same formula, just moved over to. So f of x2 plus 4 times f of x3 plus, what would that be, 1 times f of x4, right? And so on. You just keep doing that, and then you're going to add them all up. Notice that there's just a little bit of overlap, that this x2 is used here and it's used there. So when you add these all together, there's a delta x over 3 that can be factored out completely. You're going to have one of these, four of these, right? And then this one and that one get together to give you a coefficient of 2, and then a 4, and then this x4 would be used in the next one as well. So the total area is approximately equal to 1/3 times delta x times, you're going to have f of a, then you're going to have 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus, and so on down the line. It alternates 4, 2, 4, 2, 4, and the last one before the very last one will be one of these in the middle, and that's going to be a 4. So you're going to have plus 4 f of x n minus 1, and then you've got the last f of b, that very last one there. All of that is times the delta x over 3. This is what's called Simpson's rule, 4, 2, 4, 2, 4, 2. One thing I notice is that, again, you're using all the heights, but you're multiplying them by different things. With the rectangle rule, all of them got multiplied by 1, and then you just multiplied by delta x when you were done. In the trapezoid rule, the first and the last one were multiplied by 1, but all the ones in the middle were multiplied by 2, and you divided by 2. You multiplied by a half out here. Essentially, this is like the next step up. We're multiplying by 4s and 2s, 4s and 2s, 4s and 2s, and then we're dividing by 3. And the average of those 4s and 2s is 3. But for some reason, we're weighting some of them heavier than others. Anyway, this is called Simpson's Rule. Let's do the same example we did for the trapezoid rule. So I'm going to estimate the integral from 0 to pi of sine x dx. Again, I know that it's equal to 2. And we had an estimate that was good to about the second decimal place here. The error was in the second decimal place. Let's see how it works with Simpson's rule. So again, my interval here is cut up into, I'm going to use n equals 6. That is even, so I can do that. So again, I'm going to have 0. I'm going to have pi over 6. I'm going to have pi over 3. I'm going to have pi over 2. I'm going to have 2 pi over 3. I'm going to have 5 pi over 6, and then pi for my 6 cutoffs there for dividing that interval up. And my area now is approximately 1/3 times pi over 6. That's the delta x. And so then I want the sine of 0 plus 4 times the sine of pi over 6 plus 2 times the sine of pi over 3 plus 4 times the sine of pi over 2 plus, what am I, 4, 2, 4, 2 times the sine of pi over, what was next, 2 pi over 3 plus 4 times the sine of 5 pi over 6. It always is a 4 just before the very last one, which is just a 1 times the sine of pi. So, doing a little bit of work here. I got pi over 18 times. Sine of 0 is 0. Sine of pi over 6 is a half. So, sorry, 4 times a half. That's 3 pi over 2. So 2 times 3 pi. No, it's not. It's square root of 3 over 2. What am I talking about? Square root of 3 divided by 2. That's 1. 4 times 1. Plus 2 times the square root of 3 over 2. Plus 4 times a half. Plus 0. And when I type all that into my calculator and see what I get, it comes up with 2.00086 and some change. So the error this time was pretty dang small. I mean, I know this integral is 2, and Simpson's rule here worked to 1, 2, 3. I'm off in the 4th decimal place. Actually, I'm off by 0.00086. I guess I can do that subtraction pretty easily. Simpson's rule is generally more accurate than the trapezoid rule. It's interesting to me as to why that these get 4s and those get 2. Why are these more important than the other ones? But that's just an approximation using parabolas. That Simpson has already figured out the equation of the parabola. He's already integrated it for you, and he said, hey, here's what the result is. These are the things you got to multiply by in order to get this estimate. Okay? Simpson's rule.